What we have to go over today is how to write nuclear equations, how to show an unstable nucleus and the change it will undergo to become more stable. So what I'd like to do is I'd like to go back to these examples that we just did. We're going to start with the strontium-90 problem right now. So, to write a nuclear equation, I'd write its symbol, I'd write the mass number, and the atomic number. This is your standard way of showing isotopes. And we have gone over how to write this before. A nuclear equation is going to have a change to that isotope. A lot of times in chemistry, if we're indicating a change, we draw an arrow. Strontium-90 was unstable because it had too many neutrons. The way to solve too many neutrons is through beta decay. So the first thing I'm going to write on the other side of my arrow is a beta particle. Now if you want to use the big cursive B, feel free to do so. I would say in years past on our final exam, we have given the symbols to the students on like the back page of useful information, and usually we'll use the E version instead. If strontium-90 undergoes beta decay, it will become a new, more stable element. We can figure out what that element is by filling in the rest of this balanced equation. How you would do that is treat the arrow almost like an equal sign. And let's figure out the mass of the new particle. 90 equals 0 plus something. Okay, we don't need a calculator for this one. The mass of the new thing is going to be 90. Now just be careful with the next math because sometimes people will go the wrong direction. 38 equals -1 plus something. 39, yeah. So we figure out the mass number, we figure out the atomic number. Then you look at your periodic table and you figure out the symbol for that number. Why? Because we need to know the symbol for that number. Because we need to know the symbol for that number. Now, really what I did is this morning I typed in unstable isotopes, and strontium-90 was one of the first one that came up. It just happened to be a pleasant surprise that yttrium was made, so I could just do that a few times to amuse myself. This is a skill that we need to learn today. This is a skill that you will see on your final exam. This is something that we anticipate that through a little bit of practice will be one of the easier things for us to do because it's not an explanation. It's not writing a chemical equation because it's not a chemical change. It's not the same elements rearranged. It's a nuclear equation. Let's do two more. Polonium-210. Let's go with that one. Polonium is PO, 210, and 84. Nice thing about a nuclear equation, you have one thing on the quote-unquote reactant side. That's called the parent isotope. It's the thing that starts it all off. Well, why was polonium-210 unstable? It was too big. How do we undo too big? Alpha decay. Alpha particle, 4,2He. And again, if you wanted to use the A, feel free to do so, but commonly I think we use the He symbol when we do this, when we give the symbols. And once again, we treat it like a math problem, where the arrow is an equal sign. We figure out the mass of the new isotope. By the way, that new element is called the daughter product. So we figure out the mass of the new daughter product. We figure out the atomic number of the daughter product. We look at our periodic table. What element was that? Once you take about, we're going to give you 15 seconds. Figure out the mass. Figure out the atomic number. find the symbol. Daughter product for that should be lead 206. Okay? Let's do one more. Should we do the bromine 80? It's already stable. We wouldn't be doing anything. No, let's do the carbon 11. Carbon 11 is actually one of the elements that is used in PET scans. And why was carbon 11 unstable? It had too many protons. Positron emission can take care of too many protons. There's the symbol for a positron. Again, take about 15 seconds, figure out the mass of the daughter product. Figure out the atomic number. Again, be careful. Sometimes you're adding one, sometimes you're subtracting one based upon is it beta decay, is it positron emission. Silly mistakes like that is somewhat common, unfortunately. And then once you know the atomic number, you can figure out what element it has become. (11.5B) for boron is what that would become. There are more types of decay out there than this, and there's more types of nuclear reactions you can write. We might give you a little taste of them from time to time, but these three types are the three that we would assess you on when it comes time for your final exam. Since there's no unit test for this miniature unit, we're making sure that we have between 15 to 20% of your final with nuclear chemistry, the most recent stuff. I want to go over is at the bottom of that how-to sheet, it says, in a portion of the uranium decay series, lead-214 decays into bismuth-214 by beta emission, bismuth-214 decays into polonium by beta emission, polonium decays into lead by alpha emission. Write each of these steps. Some things are so unstable and they have so much wrong with them, they have to go through multiple steps in order to achieve stability. We would be writing what's called a decay series. It's something that we're going to go over a little bit more next class period as well, but I wanted to give you a little bit of a taste of that today with this how-to sheet. So for example, on that problem, it starts with the isotope of lead-214. And what it states is that it's going to go through a beta decay. So my beta particle is 0 minus 1e. And I can figure out my daughter product. It's got to be 214 for the mass and 83 for the atomic number. Which makes it bismuth, Bi. Now, if we asked you to write a decay series, multiple steps, there's two different ways you could do it. After step number 1, I could then rewrite my daughter product, 214-83Bi, and show it going through the next decay, which on this problem it says the next decay is another beta, making 214-84 PO. Now we would have to write each step independently of the other, because as you're going to learn next class period, is some steps take longer than others. And we know that amount of time, we refer to it as the half-life of an isotope. And then if I wanted to write the third step, I could rewrite 214-84 PO. The last step said it was undergoing alpha decay. So in essence, what happens is lead-214 decays into lead-210. This is one way that you could write it. There's a second way that I kind of prefer to write it that I'd show you right now. Just like stoichiometry, there's more ways to do it than one. What I would do after step number 1 is I'd see that I already ended with my daughter product here. So in other words, here is step number 1. I'm just going to draw an arrow right away and write my step number 2, which was this one here. 0, negative 1e plus my 214, 84 PO. You can see this works better if you have a lot of room. Because now here's my step number 2. And if I had enough room, then I could write my step number 3 right after the polonium. I've seen some people just kind of go down and around if they really wanted to. If I can make sense of it, I'd be okay with it. Or if you have a lot of room going across, you could do all of them at once. I would ask if you like this method instead, to always end with the daughter product at the end of each step, because then this second step right here makes sense. But if you switch this with the beta particle, a beta particle making a beta particle plus polonium doesn't quite make sense.